of web frameworks and collects them on this website and displays them. Every couple of months there's a new round, and then the results from the benchmark are displayed in a table, and you can sort and filter the results there. The source code is available in this repository. Currently there are 6 micro benchmarks, and the requirements how a benchmark is to be implemented is available at this documentation site. The requirements are verified and benchmarked also by the TFB tool in the root of this repository. All the test implementations are contributed by the community because, of course, the actual users of the frameworks know, of course, best how to implement them. And the benchmarks exercise the following features: JSON serialization, database access across 3 databases, a random number generator in the language, an array data structure and sorting it, HTML templating with correct escaping against cross-site scripting attacks, and of course what the framework does by its core, parsing the HTTP request and generating an HTTP response. 2 examples. These micro benchmarks are not very difficult to implement. This one is probably the most simple one. It generates a HTTP response with status code 200, and a content type header for the HTTP header, and the HTTP body consists of an encoded JSON object. This one is not allowed to be hard-coded because the requirements forbid it. It actually also benchmarks the performance of the JSON encoder in this case. And a complicated example, fetch all the records from a database table and put them into an array, then add another record to the array at runtime, sort the array, and in the end, create an HTML document with a templating system and render some HTML and push it out as an HTTP response. So quite simple. The following 5 frameworks are currently available in the main repo: Dancer, Mojo, Plack, and WebSimple. This is a good start, but the situation is less than awesome. Some test implementations are incomplete, meaning they do not provide all 6 benchmarks that are possible. Some implementations throw errors, so the results are meaningless. Of course, we can only accept results that are correct, because it's very, very easy to make a fast but wrong answer, right? So some tests cheat by deploying on a non-Perl web server. It's mostly pointless, because we want to see how fast Perl itself can be. And the benchmark configuration has several authors and therefore easily confuses categorization for platform, front-end web server. Yeah, this means that in the current results available on the main web page, the filters are wrongly labeled. This is the consequence of that. The test in the directory Plack is also a misnomer, because it does not use the Plack : modules, but accesses the PSGI env directly. And 5 is not a really great amount of frameworks, considering we have 40+ frameworks on CPAN alone. No, 30, and 40 web servers, or the other way around, I can't remember. So of course, if we want to test everything on everything, that would be a huge undertaking. And there are also 3 databases, as I said before. So you can see this is a lot of things to exercise, but with limited time I can't do everything. So I choose to use for subsets. The first one is taking the raw PSGI application, because it theoretically has the lowest possible overhead, because there is no routing in it, there is no automatic request parsing, and so on and so on. And just switch out the web server at the end. So we have the same application, but on several different web servers. And the other subset is extending the popular web frameworks which are available there at Catalyst, because this is a huge one by user base, but is missing in the benchmarks. And I had to postpone deployments on Apache HTTPD because I require a Docker image that is derived from Perl 5.28, because you have to first compile Perl, then compile the web server with the Perl installation, right? So, and these are the results. First, the same PSGI application across several web servers. Let's sort by average latency. And the winner is Corona, followed by Starman, followed by NetAsync HTTP server. We sort by requests per second. More is better. So here the winner is Starman, followed by NetAsync HTTP server. And the total throughput, here the winner is NetAsync HTTP server. So why did it appear here in the second place? Because the variability of the result from Starman is quite high. Or yeah, and then the other subset I chose, we don't even need to sort the results here. We can see that Kelp transfers the competition across the board. Very low latency, 2 milliseconds, followed by Dancer with 8 milliseconds. Catalyst takes 80. Request per second, 1000 per second here, followed by Dancer, only 250. And also quite strong request per second throughput. Here, the Dancer has a higher transfer rate, but Kelp is again in the second place. So this result is not that surprising, because it was already the winner in the previous rounds on the official hardware in the benchmark. Okay, future outlook. The official results, as I said before, come every couple of months. A new run is done, and the results are calculated. The code I have produced needs to still be merged into the main organization's Git master, and then they will be able to run it on their test hardware and test VM for comparison, for proper comparison, because the results I were showing on the spreadsheet is from my hardware, so it can't be directly compared to the existing numbers. Now, of course, the downside, these tests are not actually very meaningful, because it is restricted to Linux, and the point of all these different web servers are, of course, that they behave differently on different operating systems and environments. There are some that perform better on Windows, for example. And these result tables can only show which framework is fast, but not what's good, because that's the quite difficult question to answer. So this test specification should be amended to include more advanced features. For example, that which exercise concurrency code, because a number of the web servers are based on an event loop and are a target code that has that kind of concurrency inside it. But the micro benchmarks so far do not do this. And the tests should also be amended to include a larger realistic web application. Yeah. Mostly micro frameworks are not very meaningful. Anticipated questions. These results can't possibly be right. You can benchmark them yourself. You just need Docker and a fat internet connection. It will download a lot of data beforehand. And the code as shown is wrong or inefficient. Yeah, you can also contribute, re-coordinate work with on the official IRC channel, And this will be my clone of the original repository. I haven't pushed it yet. So, do you have questions or comments? Yeah.
How bad do the Perl frameworks and Perl applications compare to the other?
How bad does Perl compare to the other languages? Quite badly. There are implementations in Java running on the new VM, what's it called? Graal, and frameworks in C, and they are quite fast in these micro benchmarks.
Are they written to be fast in the benchmarks, or just generally fast?
Are they written fast to be in the benchmarks or generally? I don't know, but it's quite possible that framework authors are motivated by this benchmark when they see an opportunity to make it faster without having a different trade-off. I can imagine that they will improve their code so it benchmarks better. I think this should also be the goal for us Perl people here. Yes? Are there Perl 6 frameworks benchmarked? No, nothing. If you know Perl 6, then you can quite easily implement this code. Yes? Am I aware of any effort to improve these frameworks as a result of the benchmarks? I don't know. No, but once the numbers are available on the official site, we can send them, hey, look, framework author, this is how you do in comparison to Kelp. What's the reason? It's really quite motivating. Anyone else? No? And let's have a look at some code, just to show you that you too can contribute a benchmark test. The whole file here written in raw PSGI is just 100 lines, loading some modules, connecting to the database, setting up an HTML template, and the rest of the half of the code is just the main application. Every comparison to the path info here is a poor man's router, and each indented part here is the actual micro benchmark implementation. As I've shown before, here the JSON encoder, here doing some database queries, here the HTML templating, updating the database, and the last one, plain text. Super easy. All right, that's all from me. Thank you for your, what's the word? Attention, yeah. Thank you.